Alright, so our order of business for this evening, or I suppose I should say for the afternoon, is called Complete the Square. And you see, if you can see that, it's not in the sense of the shape so much as it is the number. Remember, a square number is essentially the product of a number times itself. So, what coincidence, or what significance could that have for us in dealing with quadratics? When you see quadratics are identified by their containing of the term x squared. So it's natural that we will talk about things that involve square numbers here. Now, let's take a look at a basic quadratic that we know. We know y equals x. Let's make it simple. X and x minus 2 and minus, how about 4? That's a good one. We know a couple of things. One, we know that there are zeros of this function whereby specific values of x create 0 for y. So positive 2 and positive 4 are those specific values for this particular function. In other words, they are the locations upon the x-axis where the parabola will cross. So, we have 2, 0, we have 4, 0. Alright? We also know that this equation can be written in standard form if we merely complete the distribution. So, x and x, the minus 2x and the minus 4x from the, as you call it, the double chin, minus 6x, and of course the negative 2 times the negative 4, positive 8. Alright, from there we know some additional information that the constant c in the format ax squared plus bx plus c yields the y-intercept 8, or the point 0, 8. So this is true for all points that are deemed to be y-intercepts have an x value of 0. So, that's a grand bit of information, right? We also know that we can begin to visualize this if we start to plot those points. Okay, so let's plot the zeros, 2, 0 and 4, 0, and of course the y-intercept up here, and we'll try to draw this one to scale, 2, 4, 6, 8. Alright, so of course this parabola is going to be open upward. It's going to have a corresponding point on the other side, which I'll show you in just a second. But from our studies about symmetry, we know that parabolas created by quadratic functions always have symmetry about a vertical line. So, if we try to sketch this out, it's going to be open up. It's going to have a vertex somewhere around here. Don't know if that's exactly the place. Wink, wink. I've got some idea. And then I'm going to take its value here. See, it's 3 away from the axis of symmetry. It's going to be at the same level. So that point's going to correspond. Of course, we could draw our arrows up, and it goes up forever and ever. Right, so what then? Oh, it's almost my bedtime. That's all right, I have an alarm, so don't forget when you get old like myself. But this is a lot of information. It's got a minimum value somewhere down here. We've got the zeros, so the x-intercepts. We've got the y-intercept. Right? We talked in class about how the vertex, if this indeed has symmetry, must lie equidistant from the x-intercepts. Most of us just say in the middle. Right, but numerically in the middle. Yes? So, what we're going to do, we're going to think about these numbers, 2 and 4. How do we find the middle of two numbers? Well, it's simple. You add them up and divide by 2. That's called finding the average, and you get 3. Well, that makes sense because the axis of symmetry here is indeed 3. Now, x equals 3 is an equation of a vertical line. Right, but how do we figure out where this point is exactly, not just the x-coordinate? And in class, we know that if we simply plug in x for 3, that will give us the location of this point. So let's do that, just so that we can review what we should already know. Don't call me Captain Obvious, okay? 3 minus 2 3 minus 4, that's going to equal negative 1. Go ahead, pause it if you don't get that. It's negative 1. So I was right. I was right. But what I want to show you today is another process that we're going to do to this standard form that will help us produce this exact point, the vertex. Okay, so what does it look like? Let's bow down from this one just a moment and let's look again at the standard form of this. Alright, so how are we to complete the square? You see, completing the square is going to be a process whereby we add and subtract a number so that we can create a perfect square binomial. And I will tell you about the form shortly thereafter. But here's what I'm about. I want to know, how can I get from here to something like this? And of course, this does not factor into two identical binomials as we see from above. So what we're going to do, we're going to add a special number, you might say, right? And of course I put the 8 out here, but of course if I add a number to an equation, I've got to subtract it right away to make sure that I don't change anything. Okay, now here is the pudding of this video. How do I choose some special number here? I'm going to give it to you. It's half this number squared. That's right. It's the b divided by 2 squared. So what we're going to do, we're going to have 6, we're going to get 3. We're going to square the 3 and we're going to get 9. So if I add 9, I've got to subtract 9. Right? Okay. That way, I haven't changed anything. Go ahead, think about it. Add 9 and subtract 9. It's a net effect of 0. So, what then, have you? What if we get the focus right? We know that x squared minus 6x plus 9 has a special way to be factored. X minus 3 and x minus 3. Isn't that what we're looking for? So let's take care of this bit down here before we get too excited. Negative 9 plus 8, that's negative 1. I know this thinking, hey, that doesn't look right. That doesn't look like anything we've done. That's why this is called learning. So, where can we go from here? Remember, this was our goal. Once we get our goal in mind, take a look at what has transpired. X minus 3 and x minus 3 can be written as x minus 3 squared. And then, of course, we get minus 1. Now, why on earth would we do this? This seems laborious, boring. But I want you to think about something. This equation, I haven't added or subtracted anything. It's the same as what it started, right? But what do we get from this equation? We get the y-intercept. Of course, you've got to factor it. You've got to do some other heavy lifting to reveal anything else. What do we get from this one? Well, it's clear that we do not get the y-intercept. But if you go back to our graph and you realize, hey, this vertex was at 3, negative 1. How does this correspond to the values you see here? You see, this is called vertex form. And it's something you've got to know. Right? There are other uses for it down the road. Of course, we'll use one to prove a very mighty formula. But this process is what we will use, one of the forms we will use, to produce the vertex of any quadratic function. Right? Right? Because all quadratic functions, all parabolas have a vertex. So, how does it work? Let me first write it for you. Y equals a, that looks familiar. Can you see that? X minus h squared plus k. Alright, focus a bit there. Get in the focus a bit there. That's right. Whereby a, of course, that's the quadratic coefficient from above, and then we enter h and k. So h, comma k are the coordinates of the vertex itself. Okay, now it looks a bit different because it's x minus, right? And then here it was x minus 3, and the vertex was at positive 3 for x. So we can't get that mixed up. We've just got to think about it. The formula is x subtract h. So think about what makes a parentheses equal to 0. right? What number would make that? And of course, h plugged in for x. H minus h is 0, squared is still 0, plus k. So what's happening there? We're actually getting the minimum possible value for something squared, which is 0. So much emphasis on 0. It's not like it's a hero or something. Alright, so let's do another. Let's take one more gander while we've got time. Y equals x squared plus 8x minus 5. Alright, that one's a bit ugly, if I don't say so myself. Right, but all I want to do is find the vertex. Of course, we get a nice y-intercept there, but that's not that important, not right now. We want to know where the vertex is. So let's take this process step by step. I'm going to write it x squared plus 8x. We're going to make a little square here. I like to do that in this process, for obvious reasons, I hope. And of course, the minus 5. So what I want to focus on is, of course, what's going on in these boxes. What number goes in there? And again, it was b over 2 squared. Or perhaps you don't like parentheses. You want to remember it this way. It's b squared over 4. b squared over 4. Right, these are equivalent, so pick one. Doesn't matter. 8 squared over 4. 64 over 4 is 16. Right, you can do it the other way as well. b over 2 is 4. 4 squared. Yep, still 16. Well, we've got to add it and subtract it because we don't want to change the equation. If you add a number to an equation, that's going to transform it. It's actually going to translate it up. So that's not what we're trying to do. We're just trying to manipulate some things to reveal some other things. So, step from there, x. Of course, this part is going to factor into these two pieces, x plus 4. Those have to be the same. If they're not, you've done something wrong. And then we have minus 16 and minus 5, so minus 21. And from there we can finish it out. Y equals x plus 4 squared minus 21. So write down where you think the vertex is. Go ahead, pause it, write it down. Alright. Now if you remember from the previous page, this was normally x minus h. So in order for h minus h to produce a positive 4, h would have to be negative 4. And of course the k, this is our k, it's just negative 21. So the vertex is at negative 4, 21. One additional thing I'd like to point out is that you can always get this really easy. You don't have to think so hard once you get here, because it's always the same. It's always going to be half of that number. Another way to look at it, since it's got to be something squared, it's always going to be the square root of this number. So square root of 16 produces a 4. So it did it for us. Alright, one last one. I think I can squeeze it in our time limit. Alright, let's do it this way. So we've got y equals x squared minus 12x. Oh, that's gnarly. So this one doesn't have a number, right? It's got factors that are kind of funky. So we're going to add a number, and then we'll subtract the same number. What number, you say? Half of 12 squared. 36. So we've got y equals x, right? It's always the square root of this number, minus 6 squared, and then the minus 36. Now, we're going to see if that matches up with our intuition from later. Right, this produces a vertex at 6, 36. So what I'm going to do, I'm going to rewrite the original function in standard form, right? And then I want you to try and see, how do I factor this? And it's really easy. So we've got a greatest common factor of x. So we have to factor that out. What's left over is x subtract 12. Right, so we've got x equals 0 and an x equals 12. So it matches up. The middle between 0 and 12 is, of course, 6. If you plug 6 into this equation, you're going to get minus 36. I'm so glad we did that, so I didn't screw that part up. Alright, hopefully you didn't get this far and forget, and you saw my mistake, and you're like, you messed it up? Okay. Anyways, we're going to use this. We're going to use this quite a lot. But I just need you to know the process to find the vertex. Good luck. Cheerio.